Hello everyone and welcome to this new lecture. In this lecture we will discuss the Laplacian operator and use of Laplacian operator in edge detection. So this derivation of Laplacian operator and derivation of this mask we have already discussed, that from Laplacian operator how do we get this mask and how that mask can be approximated to this mask. This we have already discussed in the another video. So the Laplacian can be implemented by this mask. Here the center pixel has the weight 4 and these orthogonal pixels have the weight -1 and these pixels have the weight 0. And the another variant of this is center pixel has the weight 8 and remaining all neighbor pixels have the weight -1. And here we see that the sum of all the coefficients in this mask is equal to 0 and sum of all the coefficients in this mask is also equal to 0, which results us a 0 response in the constant gray level. Okay, so these masks are isotropic for rotation increments of 90° and 45° respectively. This we have discussed while discussing the Laplacian operator, that this mask is isotropic with the rotation increment of 90 degrees. That means if we rotate our image by 90 degree, it will still result the same. And this mask is isotropic with the increment of 45 degree. So if we rotate the image in any angle multiplication of in the multiple of 45 degree, then that this mask will result in the same output. Okay, but the Laplacian has some certain limitations. So due to that, Laplacian is not used directly in its general form. So Laplacian, before we apply Laplacian, we use some other function on the image. So what are the limitations of Laplacian operator that we will discuss. So as a second order derivative, and this we know that the Laplacian is the second order derivative. The Laplacian typically is unacceptably sensitive to noise. So this we have discussed that the second order derivatives are more sensitive to noise. This is one limitation of Laplacian operator. Then magnitude of Laplacian produces double edges. So while discussing the first order derivative and second order derivative, there we had seen that the response of second order derivative response of to an edge is uh, double edges. So it gives us first a negative and then a positive value it gives us. So it gives us double response to the edge. And Laplacian is unable to detect edge direction. We cannot know the direction of the edge by the Laplacian operator. So these are some of the limitations which bar the use of Laplacian in its general form. So how do we use then the Laplacian operator to detect the edges? The role of the Laplacian in segmentation consists of using its zero crossing property for edge location. So we use its zero crossing property, which we have discussed in the previous lecture, that the second order derivative gives a positive value for dark pixels and a negative value for the brighter pixels. So we can identify the zero crossing of the edge by using the Laplacian operator or the second order derivative, or using it for complementary purpose for establishing whether a pixel is on dark side or light side of an edge. So this is how we use Laplacian operator in image edge detection. The Laplacian is combined with smoothing as a precursor to finding edges via zero crossing. So what is done in Laplacian in edge detection using Laplacian? First we use the smoothing filter and over that we apply this Laplacian operator. So that is how we use this Laplacian in finding out the hs. So if we consider this function hr is equal to minus e raised to power minus r square by 2 sigma square. So where r square is equal to x square plus y square. These are x and y are the coordinates of the image. Sigma is the standard deviation. So what will happen if we apply this function on an image? Then it will blur the image. It will blur the image, and the degree of blurring of the image will depend on this standard deviation. This standard. Now, if we take the Laplacian of this function, if we take the Laplacian of this function, then Laplacian of h. Laplacian of h means Laplacian is second derivative. So second derivative of h with respect to r, that is equal to this. So if we take second derivative of this with respect to r, we get this one. So that is called the Laplacian of h with respect to r. Now this function is commonly referred to as Laplacian of Gaussian. Now why it is called Laplacian of Gaussian is this function is a Gaussian function. If you remember the Gaussian function, it is e raised to the power minus r square by 2 sigma square. This is of this kind. So this is a Gaussian function, and we take Laplacian of this Gaussian, Laplacian of this Gaussian. So this function is called, this function del square h. This is called Laplacian of Gaussian. Now if we plot this Laplacian of Gaussian, then the Laplacian of Gaussian's mesh will appear like this. It will have a very positive, very high positive value at the center of this, and then it will have some negative values, and then it will have the zero values as the x and y increases. So this is the Laplacian of Gaussian mesh. Its approximate mask can be given by this. So here this 16 corresponds to the maximum positive value that we get here, and then nearby to this we have some negative values. So these negative values are here, these are the negative values, and then after that we have here zero values. So these are the zero values after that. This is one approximation of LoG. This is not the unique approximation of the LoG. We can have other approximations of the LoG depending on our application. Now let's read out some of the points about this. The coefficients also some the coefficients also must sum to 0 so that the response of the mask is 0 in areas of constant gray level. That means if we look at the sum of the coefficients of this mask, then it will be equal to 0. Why? Because this is 16 and this minus 2 will make minus 8, and we have minus 8 minus 1s. So total will be equal to 0. So by doing so, what we will be able to achieve, we will be able to achieve a zero response in the area where the gray level is constant. So if all the pixel values are constant in this uh, in this subimage of an image, then its response will be equal to 0. Why? Because here we have 16, here we have sum of all these coefficients equal to 0. Now the one more name is given to this LOC because of its shape. So due to its shape, the Laplacian of Gaussian sometimes is called Mexican hat function. Mexican hat function. So its mesh appears like a, a hat. So that is why it is sometimes called Mexican hat function. Now, since second derivative is linear operation. LOG is same as applying Gaussian smoothing filter first and then computing Laplacian of the result. Now, the second order derivative is a linear function. Linear function means what we can do is we can apply a Gaussian smoothing filter over the image first, and we can apply we can compute Laplacian of the result. So that is also can be done to implement LOC. To implement LOC, what can we do? We need not to apply this directly. What we can do, we can apply a Gaussian smoothing filter first, and then we compute the Laplacian of the result. That is also possible. So this is possible. Why? Because the second order derivative is linear operation. Okay, hope this is clear. Now let's take one example. So this is one original image of angiogram. So this is original angiogram image, and here this is the output of Sobel filter. So Sobel filter is applied to to uh, detect the edges in this image. So here we can see it is detecting the edges of this image. Now here, to implement the LOG, a Gaussian function is used, a Gaussian mask is used of 27 cross 27 dimension, and it is Gaussian smoothing filter, and this Laplacian filter is used. This Laplacian operator is used to implement the Laplacian of Gaussian. So this is the result of Laplacian of Gaussian. That means what is done here? Mm, First, a 27 cross 27 smoothing Gaussian filter is applied on the image, on the original image, on this image. The smoothing Gaussian filter is applied, and the dimension of the Gaussian filter was 27 cross 27, and then Laplacian of the result was computed. So this is what we have got the result, and then this image is thresholded by assigning a black to the negative value and a white to the positive value. So by doing such thresholding, we have achieved this image. And after that, this image is scanned for the black to white transition, black to white transition, and by doing so, by identifying the black to white transition, we have achieved the zero crossing in this image. So when we uh, cross a transition from black to white, that means there is a zero crossing available at that particular uh, pixel element. So that is what we have achieved here, and by doing this, if we compare, so this also gives us the edges of the original image. Now here we see that the edges which we have obtained by applying the LOG, that is Laplacian of Gaussian, these edges are thinner and finer than the edges which we have obtained by using the Sobel filters. So this that is one reason we can use this LOG over the gradient operators. Now let's read some more points about these outputs. So one straightforward approach for approximating zero crossing is to threshold the LOG image by setting all its positive values to say white and all negative values to black. So thresholding was done, as we have discussed this thresholding was done by assigning all its positive values to white and all its negative values to black. So this is thresholding was done, and after doing thresholding, the estimated zero crossings is obtained by scanning the thresholded image and noting the transitions between the black and white. So this zero crossings, this was achieved by scanning this image and noting the transitions from black to white. So by noting that, we have achieved this zero crossing in the image. We note that the edges in the zero crossing image are thinner than the gradient edges. This is a characteristic of zero crossings that makes this approach attractive. So here we have already discussed that these edges are thinner than the gradient filters. So this Sobel filter is a gradient filter. So here we see that it has quite thick edges of the image, and here the edges are thin than the gradient filter. So this is one attractive property of zero crossings. But the limitation is we see in that the edges determined by zero crossing from numerous closed loops. This so-called spaghetti effect is one of the most serious drawbacks of this method. Now, here we see many closed loops of these edges. So here all are closed loop which we get in this output. So this is called spaghetti effect which we get in the zero crossings. So this is the limitation of this LOG or zero crossing method of detecting the edges. So that is why still the gradient filters are mostly used in the edge detection. Okay, so that's it for this lecture. We will meet in the next lecture.